Please subscribe to support the channel. When people first hear that the universe is expanding, the natural follow-up question almost always emerges. Expanding into what? It's a hauntingly simple but profoundly deep paradox that has puzzled curious minds for decades. If everything we know, everything we see, and everything that exists is within the universe, then what lies beyond its edge, and how can something grow if there is supposedly nothing beyond it? This question is more than just a casual curiosity. It cuts straight into the core of modern cosmology, relativity, and philosophy. The paradox grips our imagination because, intuitively, expansion requires a container. When we watch a balloon inflate, it expands into the surrounding air. When a drop of ink spreads in water, it's expanding into the pre-existing liquid. When a city grows, it spreads into the surrounding land. Our everyday experiences anchor us to the notion that growth demands an outside, a space to move into. So when science tells us that the universe itself is expanding, our instinct is to ask, okay, but into what is it expanding? And when cosmologists answer with, into nothing, our brains immediately resist, because nothing is nearly impossible to grasp without turning it into a kind of something. This paradox isn't trivial. It has been the subject of countless books, lectures, and late-night conversations among scientists and philosophers alike. In fact, it's often one of the first questions that draws young minds into cosmology. The appeal of the paradox lies in its tension between intuition and reality. On one side, we have the familiar rules of space and expansion, and on the other, the profound alienness of cosmic truth as described by physics. To make matters even more fascinating, the paradox highlights the limits of human perception. Our everyday lives take place in 3 dimensions of space and 1 of time. Everything we build, everything we observe, everything we move, always requires a background, a stage on which the play of matter and energy unfolds. But when we scale our thinking to the cosmic level, that stage itself becomes part of the story. Space and time are not fixed arenas. They are dynamic, evolving, and subject to the laws of physics just like matter and energy. This is where the paradox takes us out of the comfortable realm of intuition and thrusts us into the profound strangeness of modern cosmology. One reason this question is so powerful as an introduction to cosmology is that it exposes the assumptions we make without even realizing it. When we hear expanding universe, we automatically import the idea of expansion from our everyday world. We picture edges, boundaries, and some kind of surrounding emptiness waiting to be filled. But the universe, by definition, contains all of space and time. If everything that exists is within it, then talking about something outside becomes slippery. It's like trying to ask, where is the edge of all directions? Or what's the color of nothing? The question itself is pushing against the limits of language. Yet, this doesn't mean the paradox is useless or unanswerable. On the contrary, it's precisely because of this paradox that cosmologists have been forced to refine their definitions and sharpen their models of the universe. Asking what is the universe expanding into opens the door to discussions of relativity, the nature of space-time, and even the philosophical boundaries of science. It's a perfect launching point for the kind of journey where we slowly peel back misconceptions, rebuild our understanding, and arrive at an explanation that is both scientifically rigorous and awe-inspiring. So as we open this long exploration, keep this paradox alive in your mind. Let it linger as a puzzle. Because by the time we've finished working through all the concepts, observable limits, relativity, dark energy, and beyond, we'll see how the question transforms. It doesn't vanish, but it reshapes into something more profound. Not what is the universe expanding into, but what does it mean for space and time themselves to expand? That reframing is where the real wonder lies. When we think about the paradox of expansion, it's easy to assume that when cosmologists say universe, they're referring to the whole of existence, absolutely everything, without exception. But here's where we need to pause and clarify, because when scientists talk about the universe in practical terms, they usually mean something slightly narrower, the observable universe. And this distinction is absolutely crucial to untangling the confusion behind our opening paradox. The observable universe is, quite simply, the portion of the cosmos that we can see, study, and measure. The cosmic horizon, bounded by the finite speed of light and the finite age of the universe. Light, as fast as it is, takes time to travel. The universe, according to current estimates, is about 13.8 billion years old. That means light emitted from the farthest galaxies we can currently observe has taken billions of years to reach our telescopes. Every photon that strikes a detector, every faint glow we record from a distant quasar, carries with it a timestamp from an unimaginably distant past. But here's where things get tricky. Because space itself is expanding, the actual distance to the farthest objects we can observe is far greater than 13.8 billion light-years. When we account for cosmic expansion, the radius of the observable universe works out to be about 46 billion light-years in every direction. That gives us a spherical region of visibility centered on us, stretching nearly 93 billion light-years across. Not because the universe itself is only that large, but because that's the furthest distance from which light has had enough time to reach us since the birth of the cosmos. So already we see a subtle but important point. When cosmologists talk about the universe, they are often talking about our observable patch of it. And here lies a limitation that is often overlooked. Beyond that horizon, beyond that 46 billion light-year radius, there could be, and almost certainly is, vastly more universe. Galaxies, clusters, voids, and cosmic structures could stretch on infinitely or terminate in some way we can't currently know. But because light hasn't had the time to carry their story to us, they remain hidden. This means that our notion of the universe is necessarily shaped by our observational limits. Now, why does this matter when we're talking about expansion? Because when we say the universe is expanding, we're speaking from within this bounded perspective. What we're really measuring is the expansion of our observable universe, the way galaxies within our horizon are receding from us, the way light stretches into longer wavelengths as space itself expands, and the way the cosmic microwave background reveals a history of density, heat, and growth. In other words, we are confined to describing cosmic expansion in terms of what's observable. This is important because it helps us avoid a common pitfall, imagining the universe as an object, like a balloon or a sphere, sitting in some larger space and growing outward. That picture arises because we instinctively think of the universe as one physical thing with a clear boundary. But the reality is that our universe is more like a sphere of vision, a bubble of what light has delivered to us. Expansion, therefore, isn't about galaxies rushing outward into some pre-existing emptiness beyond the edge of that bubble. Instead, it's about the very fabric of that bubble, the space-time itself, stretching and changing over time. Another way to think about this is to ask, if the observable universe is only a slice, what about the unobservable part? Here we enter territory of both humility and awe. Everything outside our horizon, the galaxies whose light hasn't yet reached us, might look very much like the universe we see, or it might reveal surprises that challenge our deepest models. And as time goes on, the observable universe itself changes. Every second that passes, light from slightly farther away has time to reach us, and so our horizon grows. Yet paradoxically, because of the accelerating expansion driven by dark energy, many distant galaxies are receding from us faster than light, meaning their signals will never arrive. There are entire regions of space that are permanently cut off from our view, forever beyond the observable universe, not because they don't exist, but because the rules of cosmic expansion prevent their light from ever bridging the gap. This leads us to a subtle but powerful insight. When we talk about the universe expanding, we're not describing something happening to a ball-shaped object in an external void. We're describing how the relationships between all points within our observable universe change over time, dictated by the expansion of space itself. The horizon is a limit of knowledge, not a hard wall in space. And beyond that limit, the cosmos may stretch endlessly, without requiring any outside environment to accommodate its growth. Now let's tie this back to our opening paradox. When someone asks, if the universe is expanding, what is it expanding into? Part of the confusion comes from picturing the universe as synonymous with the observable universe. We imagine the edge of that 46 billion light-year bubble as a physical boundary, like the surface of a balloon. And if there's a boundary, then there must be something beyond it, right? But in truth, the edge of the observable universe isn't a physical edge at all. It's a horizon defined by time and light. It's not the edge of existence, it's the edge of visibility. Beyond it, the universe continues, possibly infinitely, but beyond the reach of our current observational tools. So, in a way, this distinction reshapes the paradox. It reminds us that our language must evolve to match the cosmos we're describing. The universe as we experience it isn't necessarily the entirety of all that exists. It's the slice we can observe, bound by the physics of light and time. And this slice expands in a way that doesn't require an outside, because the horizon isn't a wall in the first place. By starting here, with the observable universe, we establish a foundation. We no longer have to imagine cosmic expansion as a balloon swelling into surrounding emptiness. Instead, we can begin to see expansion as a change in the scale of relationships within spacetime itself. This is the bridge that carries us forward into deeper ideas, the fabric of spacetime, relativity, and the realization that the universe's growth isn't about moving outward but about stretching inward. To grasp why the universe does not expand into something external, we need to shift from thinking of space as a container to thinking of space and time as entities that are themselves dynamic. This is where the idea of spacetime becomes central. In everyday life, we treat space and time as separate. Space is where things are, and time is when things happen. But one of the greatest revolutions in physics came from Einstein's realization that space and time are interwoven into a single, four-dimensional fabric. This fabric can bend, ripple, and expand. It is not merely the stage on which the play of the cosmos unfolds, it is part of the play itself. So when we say that the universe is expanding, what we really mean is that this fabric of spacetime is stretching. It isn't that galaxies are flying through empty void into some external nothingness, but rather that the very scaffolding that defines distance is changing. The distances between galaxies grow not because they're actively racing away from each other like cars on a highway, but because the highway itself is stretching beneath them. The road doesn't need to exist inside another road. It is complete on its own. The galaxies are not pushing into an outside. They are simply carried apart by the expansion of the metric that defines their separation. This is an idea that defies intuition, because we are so used to treating space as an empty background. When we build a house, the walls and floors are placed into space that was already there. When we drop an object, it falls through space that seems fixed. But on cosmic scales, space itself is not passive. It evolves. In Einstein's general relativity, space-time responds to energy, mass, and pressure. The presence of matter can curve space, leading to what we experience as gravity. And, crucially, the structure of spacetime can itself expand, allowing for galaxies to grow farther apart without needing any external arena to move into. Imagine this fabric not as something rigid but as something elastic, capable of stretching without tearing. The equations of relativity describe this elasticity through what's called the metric, the mathematical object that defines how distances are measured. When cosmologists say that the universe is expanding, what they mean is that the metric is changing. The scale of distance between any 2 points in the universe increases with time. No edge is required. No outside is needed. Space itself is growing in its internal geometry. One way to think about this is to return to the paradox. What is the universe expanding into? The answer lies in realizing that into is the wrong question. Expansion doesn't demand an external container any more than the increase of temperature demands a surrounding hotness to move into. Temperature can rise everywhere at once, and expansion can occur everywhere at once. The metric stretches globally, not outward into an external void. This is where the balloon analogy, which we will turn to later, begins to offer some insight, but even without it we can begin to see the universe in a new light. The galaxies we observe aren't fleeing into a pre-existing nothingness. They remain essentially in place relative to their local space, while that space itself enlarges. The expansion is not a motion through space, but of space. The philosophical implications of this are profound. It challenges the way we conceptualize existence. If space is something that can stretch, then space is not an empty nothingness but a real physical entity. And if it is real, then it can evolve, and the universe's expansion is simply the manifestation of that reality. When you hear that galaxies are tens of millions of light-years apart and growing farther away, it isn't because they're pushing into some external void. It's because the very distance between them, the definition of what a light-year means, is itself swelling with time. This understanding also illuminates why the question of an outside is so slippery. Space-time is not sitting in a larger arena. It is all that exists. To ask what lies beyond is to try to import everyday experience into a realm where it doesn't apply. There is no external emptiness waiting for space to invade. There is only the space-time that exists, governed by the rules of relativity. Expansion is a change in geometry, not a growth into something else. To make the strangeness of cosmic expansion more tangible, scientists often turn to the balloon analogy. It's not perfect, but it is one of the most effective ways to break free from the idea that the universe must be expanding into something. Picture an ordinary balloon. Before you inflate it, you take a marker and draw several tiny dots on its surface. These dots represent galaxies. Now as you slowly blow air into the balloon, the surface stretches, and every dot begins to drift away from every other dot. Importantly, none of the dots are moving on their own. They are simply carried apart by the stretching of the surface beneath them. What makes this analogy powerful is that the balloon's surface is self-contained. The dots don't need to travel into any outside arena in order to spread apart from each other. Their separations increase purely because the surface they rest on is expanding. And here's the key: the balloon's surface is two-dimensional, while our universe is three-dimensional in space. But just as the balloon's surface doesn't need an outside for its expansion to make sense to the dots, our three-dimensional universe doesn't require an external space into which it expands. Expansion happens within the fabric itself. This is difficult for us to internalize because, as external observers of the balloon, we can see the air inside and the surrounding room outside. We see the balloon embedded in a larger space. But the dots don't. To the dots, their world is only the two-dimensional surface of the balloon. They have no way to perceive the inside or the outside, nor do they need to. To them, expansion is perfectly described by the growing distances between one dot and another. For the galaxies in our universe, the situation is much the same. Their increasing separation requires no external void. The expansion is intrinsic to the space they inhabit. There's another insight hidden in the balloon analogy. Notice that as the balloon inflates, no single dot occupies a special place. Every dot sees every other dot receding from it. The same is true of our universe. There is no central point from which expansion originates. Every galaxy, from its own perspective, sees itself at the center of expansion because space stretches everywhere at once. This dissolves another misconception people often have, that the Big Bang happened at one point in space and matter exploded outward into emptiness. In reality, the Big Bang was the rapid expansion of space itself, occurring everywhere simultaneously. The balloon analogy conveys this beautifully. There is no privileged center on the surface. And yet, the analogy also highlights a subtlety that deserves attention. A balloon does have an inside and an outside. It is a three-dimensional object expanding in a larger three-dimensional space. We, as outside observers, can see this. Our universe, however, doesn't require such an embedding. It isn't sitting inside a higher dimensional room waiting to swell into the available void. The balloon analogy is meant only to illustrate the principle of distances increasing through the stretching of the surface, not to suggest that our cosmos has some literal surrounding. In fact, if our universe is truly all of existence, then by definition there is nothing outside it. Still, the balloon's lesson is invaluable. Expansion is not motion into space but the stretching of the medium itself. The galaxies don't need rocket engines to separate from one another. They are carried along by the expansion of space just as dots are carried apart by the stretching of rubber. And while the analogy breaks down if we push it too far, it offers a vivid reminder that the universe's growth can be self-contained, without edges, boundaries, or external containers. The balloon analogy, while illuminating, immediately brings us to a sticking point. Every time it's used, someone in the audience raises their hand and says, "But wait a minute, balloons have an inside and an outside. Doesn't that mean the universe must also be expanding into something, the way a balloon expands into the air around it?" And that's exactly where the analogy reaches its limit. A balloon, after all, is a familiar object in our three-dimensional world. When you inflate it, the rubber surface stretches outward into the surrounding air. The surface has an inside, filled with the air you've blown in, and an outside, exposed to the room around it. From our perspective as creatures who live in three dimensions, it's almost impossible to look at a balloon without also thinking about the environment it sits in. But that's the very perspective that misleads us when we apply the analogy to the universe. The crucial difference is that our universe doesn't require an external space in order to expand. The balloons inside and outside exist because the balloon is embedded in a larger three-dimensional room. Our universe is not embedded in any higher dimensional environment that we can point to. When cosmologists describe the expansion of the universe, they are not suggesting that space is pushing outward into some surrounding emptiness, the way rubber pushes into air. Instead, they mean that the very distances within the universe itself are stretching, without any need for something beyond to accommodate that change. This distinction feels deeply counterintuitive because our minds are wired to think in terms of containers. Everything we experience has a place. A fish swims in water. A cloud drifts in the sky. A city grows across the land. Even the air around us fills a room. Our everyday reality teaches us that things exist in something. But the universe, by definition, isn't a thing in something larger. It is everything, all of space, all of time, all of existence. To ask what the universe expands into is like asking what lies north of the North Pole. It's a question that seems meaningful at first glance but collapses under scrutiny. Returning to the balloon, imagine for a moment that you are a two-dimensional creature who can only move along the surface of the balloon. You cannot see the air inside or outside. Those concepts simply don't exist in your experience. From your perspective, your universe is the surface itself, and as it stretches, you observe all the other points drifting away. You don't need to imagine an outside to make sense of the expansion. The surface alone provides everything you can measure, and the expansion is simply the change in relationships between points on that surface. In the same way, our three-dimensional universe doesn't require an outside for expansion to be real. The balloons inside and outside belong to the analogy, not to the universe itself. The analogy is meant to break us out of the assumption that expansion must mean motion through a pre-existing void. But if we cling to the details too tightly, it can reinforce that very assumption. The real lesson of the balloon analogy is not about the air, the room, or the spherical shape. It's about the self-contained nature of expansion, how distances can grow everywhere at once, without requiring an edge or a surrounding. This is why physicists are careful to stress the limitations of analogies. They can open the door to a new way of thinking, but they cannot capture every nuance of reality. The universe is not a balloon. It has no rubber surface, no surrounding air, no inside and outside. What it does have is a dynamic geometry of space-time, capable of stretching under its own rules. And once we let go of the need for a container, the paradox that expansion must happen into something begins to dissolve. Einstein's theory of general relativity is the cornerstone for understanding why the universe doesn't need an outside to expand into. Before Einstein, most people, including scientists, thought of space and time as absolute. Newton's framework imagined them as a kind of cosmic stage, vast, eternal, and unchanging, with objects moving about on top of this fixed backdrop. In that picture, expansion really would require something to expand into, because the stage itself was thought to be rigid and eternal. But Einstein overturned that vision in the early 20th century with an idea that seemed radical at the time. Space and time are not passive containers. They are dynamic, flexible, and influenced by matter and energy. General relativity tells us that space and time are stitched together into what physicists call the fabric of space-time. This fabric is not visible or tangible in the way cloth is, but it governs how everything in the universe behaves. Matter and energy tell space-time how to curve, and that curvature tells matter how to move. It's the reason why planets orbit stars and why light bends around galaxies. Gravity, in Einstein's picture, is not a mysterious invisible force pulling objects together. It's the geometry of space-time itself guiding their motion. What's even more astonishing is that this fabric doesn't just curve. It can also stretch, compress, and evolve over time. This is the mathematical framework that allows cosmologists to describe the expansion of the universe. When we say that galaxies are receding from one another, we don't mean they're being flung through static emptiness. We mean that the metric of space, the ruler we use to measure distances, is itself changing. The scale of the universe grows, and the galaxies ride along with that growth, not because they're flying through something, but because the underlying geometry that defines distance is expanding. Imagine if you had a sheet of graph paper, and every square on the grid doubled in size over time. Two dots drawn on the grid wouldn't move relative to their own squares, but the distance between them would increase simply because the squares themselves are stretching. That's essentially what the mathematics of relativity allows. Space is not just an empty arena. It is something with structure, describable by equations, capable of changing its scale. Relativity also helps us move past the balloon's limitations. Unlike the balloon, which expands into the room around it, the universe described by Einstein's equations doesn't need to push into anything. The equations themselves define a self-contained system. They describe a geometry that can evolve entirely from within. In fact, when physicists solve the equations of general relativity for a universe filled with matter and energy, the natural result is not a static cosmos but a dynamic one. Space-time that changes with time, curving and stretching in response to its contents. This was precisely the insight that led to the modern picture of an expanding universe. Einstein himself initially resisted it. He preferred a static universe and even added a cosmological constant to force his equations to hold still. But soon after, other scientists like Alexander Friedmann and Georges Lemaitre worked out solutions that showed expansion or contraction was inevitable. Later, Edwin Hubble's observations of receding galaxies provided the evidence that the expansion was real. What had once seemed counterintuitive became the standard model of cosmology, a universe whose space-time fabric is stretching. Relativity also reveals just how alien this concept is compared to our daily intuition. In everyday life, when things move apart, we imagine motion through a medium. But in relativity, the medium itself can stretch, and that stretching can carry objects with it without requiring any outside. This is why when we ask, what is the universe expanding into? Relativity gently corrects us. It's not expanding into anything, it's expanding as itself. The fabric grows. The distances evolve. Space and time are not fixed, they are alive with dynamics, bending and stretching as the universe unfolds. And this is perhaps the most profound leap of all, understanding that the cosmos is not a play performed on a stage, but a play where the stage itself is part of the drama. The actors and the backdrop are inseparable. The story of galaxies, stars, and planets is also the story of the space and time they inhabit, woven together in the dance of relativity. One of the most persistent misunderstandings about cosmic expansion comes from imagining galaxies like projectiles being hurled outward into a void. It feels natural to think that if the universe is getting bigger, then the galaxies must be moving through space, traveling into emptiness like shrapnel from an explosion. But this picture is misleading, and it can't be reconciled with what cosmology actually tells us. The reality is subtler, stranger, and far more elegant. The galaxies aren't flying through space at all. Instead, the very definition of space, the metric that tells us how far apart things are, is changing. Let's unpack this carefully. In everyday life, motion always takes place within a framework of space that we assume is fixed. When a car drives down a highway, it is moving relative to the road. When an airplane flies through the sky, it travels through the atmosphere. Even when a rocket soars into orbit, it moves through the expanse above Earth. In each case, there is a background medium that does not itself change. Distances are constant, and objects change their positions relative to that constant. Our intuition is built on this fixed background view of motion. But on the scale of the cosmos, that intuition breaks down. Relativity tells us that the background itself is not fixed. Space-time is malleable. Its geometry can expand, and when it does, the distances between galaxies change without those galaxies needing to physically move through space. They can remain essentially at rest in their local patches of space, while the metric, the rulebook that defines what a distance means, evolves around them. This is why cosmologists describe the universe's growth not as galaxies zooming outward but as the stretching of the cosmic fabric. A galaxy a billion light-years away is not moving through space like a ship sailing through an ocean. It is being carried away as the ocean itself expands. And here's the mind-bending part. Because it's the metric that changes, galaxies can appear to recede from us faster than the speed of light without violating relativity. Nothing is outrunning light in its own neighborhood. Instead, the distance defined by space itself is growing so quickly that the separation between us and them increases faster than light can close the gap. This only makes sense if we understand expansion as a property of space itself, not as a motion through it. The difference between expansion and motion also shows up in how astronomers measure cosmic growth. When we observe distant galaxies, their light is stretched into longer, redder wavelengths, a phenomenon known as redshift. At first glance, this looks like the Doppler effect, the same way a siren changes pitch as an ambulance drives past. But in cosmology, the redshift is not caused by galaxies rushing through space. It comes from the stretching of space itself. As light travels across expanding space, its wavelength is elongated along with the fabric it moves through. This is direct evidence that expansion is about geometry, not velocity. Another way to see the difference is to imagine raisins in a loaf of bread. As the dough rises, every raisin sees every other raisin drifting farther away, not because the raisins are crawling through the dough but because the dough itself is expanding. There is no central raisin that remains still while others move away. The expansion is uniform, happening everywhere at once. Replace the bread with space, and the raisins with galaxies, and you have a more faithful analogy than an explosion in empty air. This distinction also resolves a common misconception about the Big Bang. Many people imagine it as a point of matter exploding outward into a pre-existing void, scattering galaxies across empty space. But that picture is inaccurate. The Big Bang was not an explosion in space, it was the rapid expansion of space itself. Every point in the universe today was once compressed into that hot, dense state, and the expansion occurred everywhere simultaneously. There was no single point of detonation and no external emptiness waiting to be filled. The fact that expansion is not motion has profound implications. It means there is no center of the universe, no edge from which things are flying outward. It also means that the question "what are galaxies expanding into?" becomes unnecessary. They are not expanding into anything. Their increasing separation is simply the manifestation of the metric stretching. When we replace the mental image of galaxies as projectiles with the reality of galaxies as passengers in a stretching fabric, the paradox begins to unravel. The universe doesn't need a void to grow into. Growth is not an outward journey but an internal transformation of the distances that define space itself. Expansion is not motion, it is geometry changing. And once we see it that way, the mystery of what lies outside starts to fade, because expansion is not about escaping a container. It is about the container itself growing without limit. If we want tangible evidence that the universe was once smaller, denser, and hotter, we don't have to rely solely on mathematical models or abstract reasoning. The universe itself has left us a record, a kind of afterglow written across the sky. This record is known as the cosmic microwave background, or CMB, and it is one of the most astonishing discoveries in all of science. It's not just evidence for the Big Bang, it is a photograph of the infant universe, a snapshot of reality when it was only about 380,000 years old. Today, when we look out at the night sky, we see galaxies, stars, and nebulae separated by vast gulfs of space. But roll the clock back 13.8 billion years, and things looked very different. The early universe was so hot and dense that matter couldn't clump into stars or galaxies. Instead, it was filled with a glowing plasma of particles and radiation, an opaque fog where photons, the particles of light, were constantly scattered by free electrons. Imagine a cosmic furnace where no light could travel freely, because every photon was quickly absorbed or deflected. That was the universe in its first hundreds of thousands of years. Then, around 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event is called recombination. With electrons bound into atoms, photons were suddenly freed to travel without constant scattering. In that moment, the fog lifted, and light could finally stream across the cosmos. That light has been traveling ever since, stretching as space expanded, until today it reaches us in the form of faint microwave radiation filling every direction of the sky. That faint glow is the cosmic microwave background. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB was first noticed as a persistent hiss of radio noise in their antenna. At first, they thought it was a technical issue, or even bird droppings inside the receiver. But it turned out to be the echo of the Big Bang itself. What they had stumbled upon was the afterglow of the early universe, cooled and stretched by billions of years of cosmic expansion. This discovery earned them the Nobel Prize, and it became one of the most important pillars of modern cosmology. When we map the CMB today with advanced satellites like COBE, WMAP, and Planck, we see an almost perfectly uniform glow, the same in every direction, with only tiny variations in temperature, differences of about 1 part in 100,000. Those tiny ripples are crucial. They are the seeds of structure, the slight overdensities. In the early plasma that, under the influence of gravity, grew into galaxies, clusters, and the vast cosmic web we see today. Without those tiny fluctuations, the universe might have remained a smooth soup of matter and radiation forever. Instead, those faint imprints in the CMB are the fingerprints of everything that exists. The CMB is also a clear confirmation that the universe has expanded over time. When the photons were released at recombination, the universe's temperature was around 3000 Kelvin, hot enough to glow like the surface of a red star. But as space expanded, the wavelengths of those photons were stretched, cooling the radiation. Today, after nearly 14 billion years of expansion, the CMB has cooled to just 2.7 Kelvin, only a few degrees above absolute zero. This cooling is direct evidence of expansion. It shows us that the universe was once far hotter and denser than it is now, and that space itself has stretched enormously since that early time. The existence of the CMB also debunks the old idea of a static universe. If the cosmos had always existed in its present form, there would be no reason for a faint, all-sky glow at a temperature of 2.7 Kelvin. Its very presence forces us to accept a universe with a past, a beginning, and a history of change. And the remarkable match between theoretical predictions of the CMB and its actual measurements gives us tremendous confidence in the Big Bang model. For our discussion of expansion, the CMB provides more than just evidence. It provides perspective. It reminds us that when we talk about the stretching of space, we're not indulging in abstract speculation. We are observing real consequences. The radiation that fills the cosmos is proof that space has expanded since the universe's infancy. It's not galaxies flying through a void, it's the fabric itself stretching, carrying photons along for the ride, cooling them as their wavelengths grow. The CMB is like a fossilized memory embedded in the universe, telling us not just that expansion is happening, but that it has been happening since the very beginning. And perhaps the most humbling realization is this: every time we tune into that faint microwave hum, we are listening to the universe itself whispering its earliest story. The CMB is a direct line to the moment when light first broke free, a relic from a universe unimaginably young, proving beyond doubt that the cosmos was once compact, fiery, and dense, and has been expanding ever since. By the time the cosmic microwave background was first measured, the theoretical groundwork for an expanding universe had already been laid, but it was observational evidence that truly transformed our understanding. That observational breakthrough came from the work of Edwin Hubble in the 1920s. A discovery that fundamentally reshaped cosmology and provided the first concrete proof that the universe is not static but expanding. Hubble's work began with a straightforward, yet audacious question: how far away are the galaxies we see in the night sky? At the time, astronomers debated whether the so-called spiral nebulae were part of our Milky Way or distant island universes in their own right. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the brightness and variability of Cepheid variable stars within these nebulae. Cepheids are remarkable because their pulsation period is directly related to their intrinsic luminosity. By comparing their intrinsic brightness to their apparent brightness as seen from Earth, Hubble could calculate their distance. This allowed him to demonstrate definitively that these spiral nebulae were indeed separate galaxies, far beyond the bounds of the Milky Way. Once Hubble had established distances, the next step was to measure how these galaxies were moving relative to us. He did this by examining their spectra, looking at the redshift of light emitted from these distant objects. A redshift occurs when light is stretched to longer wavelengths, and in everyday terms, it's analogous to the Doppler effect, like the pitch of a siren lowering as an ambulance speeds away. By measuring the amount of redshift, Hubble could determine whether galaxies were approaching or receding. The results were startling. Almost every galaxy Hubble examined was moving away from Earth. Moreover, the farther a galaxy was, the faster it appeared to recede. This linear relationship, now known as Hubble's law, quantified a simple but profound truth: the universe is expanding. The velocity of a galaxy, v, is proportional to its distance, d, from us, a relationship captured by the equation v equals h times d, where h is the Hubble constant, representing the rate of expansion. This discovery was revolutionary because it directly contradicted the prevailing notion of a static universe. Prior to Hubble, even Albert Einstein had assumed that the cosmos was unchanging on large scales. introducing the cosmological constant to his equations of general relativity to prevent expansion or contraction. Hubble's observations demonstrated that the universe is not static, and that the scale of space itself is increasing. The galaxies aren't moving through pre-existing space like bullets through air. Instead, space itself is stretching, carrying the galaxies along with it. Hubble's work also provided the first observational anchor for the theoretical models developed by Friedmann and Lemaitre, who had used general relativity to predict that an expanding or contracting universe was not only possible but expected. Hubble's measurements gave these models real-world confirmation, transforming them from abstract mathematics into a description of the cosmos we inhabit. The concept of the expanding universe moved from theory into observable reality. It's important to note that Hubble's discovery is subtle in its implications. While galaxies are receding from us, this recession is not evidence that we occupy a special location in the universe. Rather, every observer in any galaxy would see the same pattern: all other galaxies moving away, with more distant galaxies receding faster. This universality of expansion reflects a fundamental property of the cosmos. It is homogeneous and isotropic on large scales. There is no center of expansion, no privileged vantage point. The universe expands uniformly, and Hubble's observations were the first clear demonstration of this remarkable property. Hubble's law also provides a practical measure of cosmic time. By inverting the Hubble constant, cosmologists can estimate the age of the universe, assuming expansion has been reasonably uniform over time. Although refinements are necessary to account for variations in expansion rate due to dark energy and other factors, Hubble's work laid the foundation for what we now call the cosmic distance ladder, a hierarchical framework for determining distances across vast scales of space. Finally, Hubble's discovery beautifully complements the other pieces of evidence we've discussed. The cosmic microwave background shows that the universe was once hot and dense. Hubble's observations show that it is now vast and ever-expanding. Together, they form a narrative, a universe born from a singularly dense and hot state, stretching across space-time, with the very fabric of reality itself carrying galaxies apart. Hubble transformed an abstract mathematical possibility into a vivid cosmic reality, giving us the observational proof that the universe is not static but alive with expansion. One of the most counterintuitive consequences of Hubble's discovery is that the universe has no center of expansion. Unlike an explosion we might observe on Earth, where debris flies outward from a single point, the universe does not expand from a central location in space. There is no cosmic center from which galaxies are fleeing, and no edge from which space spreads outward into emptiness. Instead, expansion occurs uniformly everywhere at once. To grasp this, it helps to return to the balloon analogy, but now in a more precise light. Recall the two-dimensional surface of a balloon with dots representing galaxies. As the balloon inflates, every dot moves away from every other dot. Importantly, no dot occupies a privileged position. From the perspective of any individual dot, all other dots appear to be receding. There is no center on the surface of the balloon itself. The expansion is intrinsic to the surface, not dependent on any external space. The analogy is not perfect. Our universe has 3 dimensions of space rather than 2, but the principle holds. Expansion is a property of the fabric of space itself, happening everywhere simultaneously. This universality is reflected in Hubble's observations. When astronomers measure the redshift of galaxies in every direction, they find a consistent pattern. The farther away a galaxy is, the faster it appears to recede. This linear relationship holds in all directions, regardless of where the observer is located. Every galaxy, therefore, sees the same expanding pattern. There is no preferred vantage point, no special galaxy at the center. Expansion is a global property of the universe, not a motion away from a single origin in space. This idea can feel deeply counterintuitive because we naturally try to imagine an outside perspective. When we see fireworks explode, we know there is a center. When a balloon inflates, we can see the air pushing outward from our viewpoint. But the universe does not exist in a larger 3-dimensional space that we can observe from the outside. There is no cosmic vantage point from which we could identify a center. Asking where the universe is expanding from is, in a literal sense, meaningless. There is no external reference frame to anchor such a location. Mathematically, this is captured by the principles of homogeneity and isotropy, assumptions that underlie the standard cosmological model. Homogeneity means the universe is roughly the same at every location, on large scales. Isotropy means it looks roughly the same in every direction. If expansion occurred from a central point, these assumptions would be violated. The universe would have a preferred location and a preferred direction. Instead, observations confirm that large-scale expansion obeys these principles. Every galaxy experiences expansion in the same way, and the metric that defines space stretches uniformly across the cosmos. This also helps clarify a common misconception about the Big Bang. Many people imagine the Big Bang as a single explosion from a point in empty space. In reality, the Big Bang occurred everywhere simultaneously. Every region of space was once part of that hot, dense early state, and every region has been expanding ever since. There was no singular point in three-dimensional space from which everything erupted. The Big Bang was not an event in space, it was an event of space, and space itself expanded from the very beginning. Understanding that there is no center also has philosophical implications. It reinforces the idea that the universe is self-contained, with no outside to expand into and no privileged vantage point. It challenges our intuitions about motion, distance, and location, reminding us that the cosmos operates under rules far beyond everyday human experience. Distances grow, galaxies recede, and yet there is no origin point in space itself, only the evolving geometry of space-time that governs all of it. In short, the absence of a center of expansion is not a quirk or a curiosity. It is a fundamental property of the universe. It tells us that expansion is a global, intrinsic feature of space-time, occurring everywhere at once. Galaxies are carried apart not from a central location but through the stretching of the fabric that surrounds them. This realization reshapes the way we think about the cosmos. The universe doesn't grow outward into emptiness. It grows everywhere, simultaneously, from within itself. Once we accept that the universe has no center and expands everywhere at once, a natural question arises. How big is the universe? Can it be infinite, or is it finite? And if it is finite, how does it expand without an edge? These are profound questions, because the size and topology of the universe determine how we understand expansion, boundaries, and even the ultimate fate of everything that exists. Modern cosmology recognizes two broad possibilities. The universe could be finite but unbounded, or it could be infinite and still expanding. Both scenarios are mind-bending in their own way, yet both are consistent with the mathematics of general relativity. Let's first consider a finite but unbounded universe. This may sound paradoxical, but it is entirely plausible in the framework of curved space. In this model, space is finite in volume, yet it has no edges. To visualize it, think of the analogy of the two-dimensional surface of a sphere. The surface of the Earth is finite. You can measure its total area, but it has no edge. If you start walking in one direction, you can keep going indefinitely without ever encountering a boundary. You never fall off the planet. You simply keep moving along its curved surface. In a similar way, a three-dimensional universe can be finite but unbounded. Its geometry might be positively curved, like a higher dimensional sphere, so that if you traveled far enough in one direction, you could eventually return to your starting point. Expansion in such a universe does not require an outside to push into. As the space itself stretches, the distances between points increase, and yet there is no edge or external container. The universe grows internally, and the volume of space increases without any need for a surrounding void. Finite, unbounded space offers a remarkable way to reconcile our intuitions about expansion with the absence of boundaries. If the universe is curved in this way, it can be both limited in size and yet limitless in experience. The scale factor, the measure of how distances grow over time, simply increases, stretching the space along its intrinsic geometry. Every point moves away from every other point in the same way, and expansion remains uniform. The concept of a center is meaningless because there is no preferred point in this curved, finite cosmos. On the other hand, the universe could be infinite. This possibility is equally fascinating and equally counterintuitive. An infinite universe has no edges and no boundary in any direction, meaning that no matter how far you travel, you never encounter an end. Even in an infinite universe, however, expansion is still meaningful. Space itself can stretch everywhere at once, increasing the distance between points without requiring any external container. In this scenario, Expansion does not make the universe bigger in the sense of adding new territory. Instead, it changes the scale of distances within an already boundless cosmos. The mathematics of general relativity accommodates both finite and infinite models. The Friedmann equations, which describe how the universe evolves, allow for universes with positive curvature, finite, zero curvature, flat, and negative curvature, infinite. Observations from the cosmic microwave background and large-scale structure surveys suggest that the universe is very close to flat, which means it could be either extremely large and finite or infinite. Either way, the key point remains: expansion occurs uniformly, without a center, and without the need for external space. This dual possibility forces us to think beyond ordinary human intuition. We are used to imagining growth as occurring within a container, whether finite or infinite. But with the universe, the container is the space itself. In a finite but unbounded universe, there is no edge to grow into. In an infinite universe, there is no limit to growth. In both cases, expansion happens internally, as the metric defining distances changes. Our usual sense of larger is transformed. Growth is not toward something else, but a stretching of everything that already exists. Moreover, these models underscore the subtlety of cosmological observation. Because our view is limited to the observable universe, we cannot definitively distinguish between a finite universe that curves back on itself and an infinite universe that extends forever. The observable patch may be just a tiny part of an infinite expanse, or it may be a significant fraction of a finite but unbounded whole. Either way, the physics of expansion, stretching space, increasing separation between distant galaxies, and evolving geometry, remains consistent. Thus, whether finite or infinite, the universe can expand. Expansion does not require an external void or an edge to grow into. Instead, the metric itself stretches, altering the distances between points across the cosmos. Finite or infinite, curved or flat, the universe carries all of its contents along with it in a cosmic dance dictated by the structure of spacetime itself. Our intuition struggles because we are used to objects growing within pre-existing space. But the universe teaches us that space itself is the growing entity, and everything embedded within it moves along for the ride. To better visualize the idea of a finite but unbounded universe, we can return to the classic analogy of the Earth's surface. This analogy is deceptively simple yet profoundly illuminates how a universe can have a finite volume without any edges. Imagine walking on the surface of the Earth. The planet has a definite size, measurable in square kilometers, yet as you journey in any direction, you never encounter an edge or a boundary where you could fall off. The surface curves back on itself, creating a self-contained geometry. This is exactly the intuition behind a finite but unbounded universe. In this analogy, the surface of the Earth represents a two-dimensional space, while our universe has three dimensions of space. Just as the surface is finite but unbounded, the universe could have a finite three-dimensional volume while still lacking any edge. The key idea is that curvature allows space to loop back on itself. You can travel in one direction indefinitely, and in principle, you could eventually return to your starting point, much as you could circumnavigate the globe. The absence of a boundary is intrinsic to the geometry. The universe doesn't need an external space to expand into because it has no edge. Now, consider what happens if the Earth's surface were to expand in this analogy. Imagine that, somehow, the entire globe were uniformly stretching, so that the distance between any 2 points increased over time. Mountains, cities, and oceans would grow farther apart, but there would still be no outside into which the surface expanded. The Earth's surface itself would stretch, carrying everything on it along with it. Similarly, in a finite but unbounded universe, expansion does not occur into pre-existing empty space. Instead, the distances between galaxies and clusters grow as the metric of space itself stretches. The universe is growing internally, not outward into a void. This analogy also helps us resolve the misconception that expansion implies a center. On the Earth's surface, there is no central point from which all distances increase. Every observer sees other points moving away as the surface stretches, but no observer occupies a special location. The same is true in a finite but unbounded universe. Every galaxy sees other galaxies receding, and the increase in distance is uniform. Expansion is not about moving away from a central location. It is about the scale of space itself increasing. One subtle but important insight from the analogy is that the universe's expansion is metric expansion, not physical motion through space. In our analogy, cities drawn on the surface of the Earth are carried apart by the stretching of the surface, not because they themselves are moving. The same principle applies to galaxies. They are not flying through pre-existing emptiness, they are carried along as the geometry of space itself changes. This is why the edge or outside is irrelevant. The universe doesn't need somewhere to expand into. The distances are increasing because the ruler itself, the fabric of space, is growing. Moreover, the finite but unbounded model has fascinating implications for cosmic topology. In principle, light could travel around such a universe and return to its starting point, just as an airplane circumnavigates the globe. Observationally, this could lead to repeating patterns in the cosmic microwave background or multiple images of the same distant object. While current observations suggest that the universe is extremely flat and any curvature is minimal, the finite but unbounded possibility remains consistent with general relativity. The Earth analogy gives our minds a way to grasp this geometry intuitively, even if three-dimensional space is harder to visualize. Another lesson from this analogy is about perspective. Observers living on a curved surface, or within a curved three-dimensional universe, would have no way of detecting an edge simply by traveling in one direction. All measurements of expansion would look the same, the distance to every other point would increase, and the relationship between points would obey the uniform stretching of space. The finite but unbounded model preserves the homogeneity and isotropy of the cosmos while avoiding the paradox of an edge or external container. Finally, the analogy emphasizes the self-contained nature of cosmic expansion. Just as the Earth's surface can stretch without spilling into a surrounding void, the universe can expand without any external space. Distances between galaxies grow not because the universe is moving outward, but because the space within it is stretching. The universe carries all of its contents along in this expansion, and there is no boundary beyond which the growth occurs. The finite but unbounded model captures the essence of cosmic expansion in a way that is both mathematically consistent and intuitively satisfying, bridging the gap between abstract geometry and human understanding. The concept of an infinite universe expanding stretches intuition even further, because our everyday experience is rooted in finite objects that grow only when they move into some surrounding space. But in cosmology, even an infinite universe can undergo expansion, and this is one of the most remarkable and counterintuitive aspects of cosmic evolution. To grasp it, we must separate the idea of size in the conventional sense from the concept of the metric, the ruler that defines distances between points in space. Imagine an infinite flat sheet of rubber extending endlessly in all directions. If you were to stretch that sheet uniformly, every pair of points on the sheet would move farther apart. No point has a special position, and yet every point sees all others receding. Crucially, the sheet doesn't need a larger rubber sheet outside it to stretch into. The expansion happens internally, because the distances defined by the sheet's geometry increase. This is precisely analogous to an infinite universe. The universe doesn't need an external container to grow. Distances between galaxies and cosmic structures increase because the space between them is stretching, not because the universe is moving into anything beyond its own bounds. Mathematically, this is captured by the scale factor in cosmology. The scale factor, often denoted as a t, quantifies how distances between fixed points in the universe change with time. Even if the universe is infinite, the scale factor can grow, meaning that any two galaxies that are far apart today were closer together in the past. The infinity of the universe does not prevent this growth. It simply means that the number of points is unbounded, and the stretching occurs everywhere simultaneously. In other words, expansion is a local property of the metric applied globally, and infinity does not constrain it. This notion also illustrates why questions about an outside become meaningless. In an infinite universe, there is no edge to expand beyond. The universe is boundless from the outset, and yet the separation between points continues to increase. It is not like pouring water into a container. The expansion is intrinsic, built into the fabric of space itself. The room to grow is not provided by anything external. It is provided by the nature of space. Infinity does not require or preclude expansion. It simply sets the stage for a boundless, ever-stretching cosmos. The infinite model has practical implications as well. Even though the universe may be infinite, the observable universe remains finite, limited by the speed of light and the age of the cosmos. Within this finite horizon, galaxies recede, structures evolve, and the cosmic microwave background provides a fossil record of a smaller, denser past. Beyond our horizon, the universe may continue indefinitely, expanding according to the same rules. In principle, this means that for every galaxy we observe, there are countless more beyond our view, and all are participating in the same metric expansion. The infinite universe is not static or frozen. It is dynamic and evolving just like any finite universe. Interestingly, the concept of an infinite expanding universe also raises profound philosophical and probabilistic questions. If the universe is infinite, every possible arrangement of matter consistent with the laws of physics may exist somewhere, an idea explored in cosmology and statistical mechanics. Expansion then applies not only to distances but also to the scope of potential configurations. While these considerations are speculative, they underscore the radical difference between cosmic expansion and familiar, terrestrial notions of growth. The infinite expansion model also reinforces the distinction between motion and expansion. Galaxies are not traveling into an infinite void. Rather, the infinite space itself stretches, and galaxies move apart as a result. Just as in a finite universe, expansion is intrinsic to the geometry of space, not the motion of objects through it. The metric changes, distances grow, and the universe expands internally, without requiring any external reference. In summary, whether the universe is finite or infinite, expansion is possible and indeed inevitable according to general relativity and observational evidence. An infinite universe may seem beyond comprehension, yet it behaves according to the same principles as a finite, unbounded universe. Distances grow, the scale factor increases, and every region sees all others receding. There is no edge, no outside, and no center, only the continuous stretching of space itself. This understanding challenges intuition but unifies the concepts of cosmology. The universe expands because space is dynamic, not because it needs somewhere to go. To describe the expansion of the universe in precise, quantitative terms, cosmologists rely on a concept called the scale factor, usually denoted by a t. The scale factor is a function of time that encodes how distances between points in the universe change as the cosmos evolves. Unlike everyday distances measured with a ruler, the scale factor is a property of the geometry of space itself. It tells us how the metric, the mathematical structure that defines separation between objects, is stretching over time. Consider two galaxies separated by a certain distance today. The scale factor at this moment is often normalized to 1, so that their current separation corresponds directly to their proper distance. If we look back in time, when the universe was younger, the scale factor was smaller. This means the same two galaxies were closer together in the past, and conversely, in the future, if the universe continues to expand, the scale factor will be larger, indicating greater separation. The beauty of the scale factor is that it abstracts away from whether the universe is finite or infinite, allowing us to describe expansion uniformly across all cosmic scales. The evolution of the scale factor is governed by the Friedmann equations, derived from Einstein's general relativity. These equations relate the expansion rate to the energy content of the universe, matter, radiation, and dark energy. In essence, the scale factor grows faster or slower depending on the relative amounts of these components. When the universe was dominated by radiation, expansion occurred more slowly. When matter dominated, it slowed further due to gravitational attraction. Today, with dark energy dominating, the scale factor is accelerating, causing the distances between galaxies to increase faster over time. The scale factor also gives rise to the Hubble parameter, which quantifies the instantaneous rate of expansion. Hubble's law, the observational relation between distance and recession velocity, can be expressed as v equals h, t, \d, where h, t, is the Hubble parameter at time t and d is the distance between 2 points. Because the scale factor changes over time, so does h, t, capturing the dynamic nature of cosmic expansion. This framework allows cosmologists to connect the observed redshifts of galaxies with a precise model of the universe's growth, linking observations to theory. Another remarkable aspect of the scale factor is that it directly explains why the universe appears different at different epochs. Light emitted by a distant galaxy travels through expanding space, and during that journey, the wavelength of the light stretches in proportion to the scale factor. This stretching is observed as the cosmological redshift, a cornerstone of observational cosmology. By measuring redshift, astronomers can infer how the scale factor has evolved, essentially reading the history of cosmic expansion from the light of galaxies and the cosmic microwave background. Even though the scale factor is a mathematical abstraction, it provides an elegant way to reconcile intuition with the counterintuitive behavior of the universe. Whether the universe is finite, infinite, flat, or curved, the scale factor grows over time, capturing the essence of expansion. It shows that galaxies recede not because they are moving through space, but because space itself stretches, and distance is defined by the metric increase proportionally. Ultimately, the scale factor is more than just a tool for equations. It is a conceptual bridge that connects the stretching of space to the observational evidence we see in the night sky. It unifies finite and infinite models, explains cosmic redshift, and provides a way to quantify the evolution of the universe from the hot, dense state observed in the CMB to the vast, accelerating cosmos we inhabit today. Through the scale factor, we can trace the growth of the universe mathematically and conceptually, illustrating that expansion is an intrinsic property of space itself, independent of edges, centers, or external voids. One of the most persistent misconceptions about cosmic expansion is the idea that the universe needs room to grow. It's easy to fall into this trap because in our everyday lives, growth almost always implies a container. A balloon expands into air, a plant grows in soil, water fills a bucket. We naturally extrapolate this intuition to the cosmos and imagine that space itself must be embedded in a larger, pre-existing void. But this is fundamentally wrong. Space is not inside anything. Space is. The mistake comes from thinking of space as a passive backdrop in which objects move. We are used to measuring distances with a fixed ruler, imagining that if something grows, it must occupy new territory. But in the context of general relativity, distances are not measured with a universal, unchanging ruler. They are defined by the metric, which itself is dynamic. When the universe expands, it is not adding new space into some external void. It is the metric that stretches, increasing distances between points already existing within the fabric of space-time. There is no outside needed. Returning to analogies can help, though carefully. Imagine the classic balloon analogy again. The dots drawn on the balloon surface move apart as it inflates. It is tempting to think of the air surrounding the balloon as necessary for expansion. In reality, that air is entirely irrelevant to the analogy. What matters is that the surface itself stretches. Now, in our three-dimensional universe, there is no higher dimensional air or void. The expansion is intrinsic to space itself. Space is the container, the metric, and the medium all at once. There is nothing outside it because, by definition, outside would imply something beyond all that exists. There is no such beyond. Another way to see this is by considering the finite but unbounded universe. In that model, the universe has a measurable volume but no edge. As space expands, every point moves away from every other point, yet there is no external arena into which it grows. The distances increase, but there is no boundary to push against. Even if the universe is infinite, the same principle applies. Expansion occurs everywhere simultaneously, stretching the infinite fabric, not into anything else, but within itself. The misunderstanding often leads to questions like, what is the universe expanding into? The answer is that the question is misguided. Expansion does not require an external container because space itself is the growing entity. Galaxies are carried apart not through motion in pre-existing emptiness but by the changing scale of space itself. The universe is not moving into anything. It is expanding internally. Dark energy, which accelerates this expansion, further reinforces the point. Dark energy does not push the universe into a void. It stretches the fabric of space itself, increasing the distances between galaxies at an accelerating rate. Observations of distant supernovae and the cosmic microwave background show that this expansion is uniform and intrinsic, not the result of an external force or space into which the universe must grow. The universe is self-contained, and its growth is a property of space-time itself. This misconception highlights how human intuition, shaped by finite, three-dimensional experience, struggles to comprehend the nature of cosmic space. We assume that growth requires room, but the universe operates on a different principle. Space is the medium, and it stretches internally. The universe does not require an outside, because there is nothing beyond the totality of space-time. Expansion is a property of space itself, not of space in a larger space. Recognizing this is crucial for understanding modern cosmology. It allows us to discard the mental picture of the universe as a balloon inflating into air and instead embrace the more accurate, if counterintuitive, image of a self-contained, stretching fabric. Distances between galaxies increase not because space is pushing into anything, but because space itself evolves. Space is not in space, it is space. The universe grows from within, and this understanding resolves much of the seeming paradox surrounding expansion. As we observe the universe more closely, we encounter a phenomenon that challenges even the most imaginative of analogies: dark energy. This mysterious component of the cosmos is not something we can see directly, but its effects are unmistakable. In the late 1990s, astronomers studying distant Type Ia supernovae discovered that the expansion of the universe is not slowing down, as would be expected if gravity were the only force at work. Instead, the expansion is accelerating. This was a revelation, and the simplest explanation consistent with general relativity is the existence of a repulsive energy inherent to space itself: dark energy. Dark energy is not like a force pushing galaxies through space into some external void. There is no air outside the universe that it is blowing into. Instead, dark energy is a property of space itself. It acts uniformly across the cosmos, stretching the very fabric of space-time and causing the scale factor, the measure of cosmic distances, to increase at an accelerating rate. In other words, it magnifies the intrinsic expansion of the universe rather than propelling matter through pre-existing space. Every cubic meter of space contains this energy, and as space stretches, the energy density remains nearly constant, driving further expansion. To visualize this, we can refine the balloon analogy one more time, but with caution. Imagine that the surface of the balloon itself possesses a kind of internal energy that causes it to stretch faster over time. The dots on the surface, the galaxies, don't move on their own, they are carried along by the stretching surface. The rate at which the surface expands increases, but it does so without any external air or container. This mirrors the effect of dark energy. The stretching of space accelerates, and the galaxies are carried apart, not by motion, but by the changing geometry of space itself. Dark energy also helps explain why distant galaxies appear to recede faster than light without violating relativity. Since the expansion is of the space between galaxies, not motion through space, nothing is locally exceeding the speed of light. Yet, over vast distances, the stretching of space can cause separations to grow at superluminal rates. This acceleration is a natural consequence of dark energy, which has a nearly constant density throughout the universe. Unlike matter or radiation, which dilute as the universe expands, dark energy remains constant, so its influence grows in proportion to the scale of space, driving ever faster expansion. The discovery of dark energy profoundly changed cosmology. It suggests that the fate of the universe is dominated not by gravitational collapse or slowing expansion, but by an accelerating, stretching fabric of space that will continue to grow at an increasing rate. Galaxies, even those currently bound to clusters, may eventually drift beyond our observational horizon, carried apart by the expansion of space itself. This is a dramatic reminder that expansion is not just an inert, slow stretching, but a dynamic process influenced by energy inherent to space. Crucially, dark energy underscores the idea that the universe does not expand into anything. Its effects are entirely intrinsic to the geometry of space-time. The energy of empty space drives the acceleration, modifying the scale factor over time. There is no external container needed. The universe grows from within, and dark energy ensures that this growth can accelerate indefinitely. It is as if the fabric of reality itself possesses a built-in tendency to stretch, and everything within it, galaxies, clusters, and cosmic structures, is carried along in that expansion. Understanding dark energy also helps resolve the common misconception that the universe's expansion must involve motion into a void. If expansion were a process of moving into an empty container, acceleration would require some external force. In reality, the acceleration comes from within the fabric of space itself. Dark energy modifies the equations of general relativity to produce faster stretching of space between objects. Distances increase, the scale factor grows more rapidly, and yet there is still no outside. The universe remains self-contained, with expansion as a property of the space-time metric. In short, dark energy is a cosmic agent of intrinsic growth. It drives the accelerated expansion of the universe, not by pushing matter through pre-existing emptiness, but by stretching the very geometry of space. It highlights that expansion is a property of the universe itself. Space is growing, and everything within it is carried along. The acceleration reminds us that the cosmos is not static, not merely vast, but dynamic, and that the expansion of the universe is an ongoing process woven into the very fabric of reality. One of the most mind-bending questions people ask when thinking about the universe is, what lies beyond it? At first glance, it seems straightforward. If the universe is expanding, surely there must be something outside into which it grows. But when we examine the concept carefully, we realize that nothing outside the universe is profoundly different from ordinary empty space. Empty space, as we know it, still has properties. It has dimensions, it can be curved by mass and energy, it can contain fields, radiation, or even dark energy. True nothing, however, is the absence of space, time, and dimensions themselves. It is a state in which the very concepts that define existence cease to exist. In other words, when cosmologists speak of the universe having no outside, they do not mean that the universe is surrounded by empty void or a vast region that is simply devoid of matter. That would still be something: space, a medium, or a dimensional framework. Outside the universe, there is literally no space to measure, no time to flow, no axis along which to place objects. The universe is all that exists, and the beyond is not a location, a container, or a backdrop. It is an absence so complete that our minds struggle to form a concept for it. This distinction helps clarify why thinking of the universe expanding into something is misleading. Expansion does not occur in a pre-existing vacuum, because there is no pre-existing vacuum. The very expansion is the stretching of space itself. There is no external reference point, no external room, and no surrounding dimensions. Asking what is outside is like asking, as physicist John Barrow once noted, what is north of the North Pole? There is no meaningful answer because the question presupposes a framework that simply does not exist. The difficulty arises because human intuition evolved to handle 3 spatial dimensions and a single temporal dimension. We understand empty space as a volume in which things exist, but we cannot truly conceptualize a state without dimensions or time. Nothingness in the cosmological sense is not a vacuum waiting to be filled. It is the absence of the very fabric in which existence occurs. It is not a place, it is a conceptual limit, a boundary of definition rather than a physical boundary. This understanding also reframes our ideas about beginnings. When cosmologists say the universe started with the Big Bang, they are not suggesting that matter and energy exploded into pre-existing emptiness. They mean that space, time, and the contents of the cosmos all emerged together from a state in which there were no separate dimensions or measurable distances. The Big Bang was the origin of the metric itself, the unfolding of space-time, and the creation of the universe as the totality of everything that exists. Even in the case of finite but unbounded models, or infinite models, the notion of outside remains irrelevant. Expansion does not require a surrounding void because space itself is all-encompassing. When space stretches, distances increase internally. There is no need to push against anything, because there is nothing beyond the universe in which expansion could occur. What lies beyond is not an empty expanse, but the complete absence of space and time, a state that defies our everyday experience and challenges the imagination. Thinking about true nothingness also emphasizes the elegance of modern cosmology. The universe, finite or infinite, expanding or curved, is self-contained. The rules of physics, the metric of space, the flow of time, all exist within the universe itself. There is no external frame of reference, no backdrop, no higher-dimensional space needed to account for growth. In that sense, the universe is unique. It is all there is, and its expansion is an intrinsic property of its own existence. Reflecting on the nature of nothing highlights the limits of human intuition. We instinctively search for containers, boundaries, and edges because that is how our brains evolved. But the cosmos operates under rules far beyond everyday experience. The universe grows, stretches, and evolves without a place to grow into, because it is the totality of existence. Outside it, in the sense of an external location, there is literally nothing, not empty space, not a void, not even time. The nothing beyond the universe is the absence of the very framework that makes any beyond possible. One of the most striking challenges when trying to understand the expansion of the universe is that it defies our natural intuition. Human brains evolved to navigate a world of 3 spatial dimensions and relatively slow-moving objects. Our survival depended on quickly estimating distances, speeds, and trajectories of things we could see and touch. As a result, we are exceptionally good at understanding objects moving through space, the concept of containers, and cause and effect relationships in a limited, 3-dimensional environment. But these skills are tuned for everyday scales, from catching a ball to walking across uneven terrain, not for comprehending a universe that spans billions of light-years or the stretching of the fabric of space-time itself. This evolutionary limitation explains why the universe feels paradoxical to us. It's natural to picture the universe as a giant sphere or balloon expanding into pre-existing emptiness. Our intuition insists on edges, centers, and a background into which things move. When cosmologists tell us that space itself stretches, that there is no center of expansion, and that nothing exists outside the universe, it contradicts our sensory-based reasoning. Our brains struggle with a reality that is both vast and abstract, where distance and motion are defined by geometry rather than by physical travel through a medium. Consider, for instance, the concept of an infinite universe expanding. In everyday life, infinity is not something we can experience. We encounter limits everywhere. The idea that distances in an already infinite space can continue to grow uniformly seems paradoxical. Yet, mathematically, it is perfectly consistent. Using general relativity and the cosmological metric, expansion is captured by changes in the scale factor, which stretches distances between objects according to precise rules. Infinity does not preclude expansion. It only modifies our intuition. The universe can be boundless, yet its points can recede from each other at measurable rates, all in accordance with consistent equations. Similarly, the notion that the universe has no center runs against instinct. Everywhere we observe, things appear to move outward relative to us. In ordinary contexts, this would suggest we occupy a privileged position. But the uniform expansion of space is isotropic. Any observer, in any galaxy, would measure the same pattern. Mathematically, this arises naturally from the solutions to Einstein's field equations under the assumption of a homogeneous, isotropic universe. Conceptually, it challenges our instinct to look for a point of origin in space, yet it is fully consistent with both theory and observation. Even the idea of nothing outside the universe pushes the limits of comprehension. In daily life, nothing is just an empty container, like a vacant room. True nothingness, as defined in cosmology, is the absence of space, time, and dimensions altogether. There is no frame of reference, no location, no time to mark events. Our intuition cannot grasp this, because it evolved in a universe where space and time are omnipresent and immediate. But mathematically, this concept is consistent. General relativity describes space-time as a self-contained metric, with no requirement for an external substrate. The equations function perfectly well without an outside, demonstrating that our intuition is not a reliable guide at cosmic scales. Another example of our intuition's limits is dark energy and accelerated expansion. In everyday experience, motion requires a force. Objects do not spontaneously accelerate without cause. Yet dark energy produces accelerated expansion across billions of light-years without a force in the classical sense. It is a property of space itself. The equations of general relativity incorporate dark energy as a cosmological constant or a dynamic field. While it may feel unnatural to our senses, it is entirely consistent within the mathematical framework of cosmology. Our intuition simply fails when applied to a realm vastly larger and more abstract than the human scale. These limitations remind us that many cosmic paradoxes arise not from flaws in physics, but from the mismatch between human perception and the underlying reality. Our brains evolved for survival in a very small corner of the universe, not for reasoning about billions of light-years or the curvature and stretching of space-time. The universe operates according to consistent mathematical laws, yet it can appear counterintuitive or paradoxical to our senses. Concepts like expansion without an outside, infinite yet growing space, and a universe with no center are not only plausible, they are predicted by theory and confirmed by observation. Recognizing the limits of human intuition is liberating. It allows us to accept that cosmic phenomena may not make sense in everyday terms but are nonetheless real and measurable. It also underscores the power of mathematics and observation as tools that extend our understanding beyond the confines of evolved perception. The universe does not conform to our instincts, it conforms to its own laws. And through careful reasoning, experimentation, and observation, we can comprehend and describe a reality that is far grander and stranger than anything our senses alone could imagine. When we try to probe what lies outside the universe, we quickly encounter a philosophical dimension to cosmology, one that challenges the very way we frame questions about existence. Asking what is outside the universe is not merely difficult, it may be fundamentally meaningless, in the same way that asking what is north of the North Pole is meaningless. The North Pole is defined as the northernmost point on Earth. There is no north beyond it because the coordinate system itself ends there. Similarly, the universe, by definition, encompasses all of space, time, matter, and energy. There is no external reference frame, no container, no beyond in which to situate an outside. This philosophical insight is more than a clever analogy. It has deep implications for how we understand cosmology. When humans first imagined the universe as a finite container, it was natural to ask what lay outside, just as someone might wonder what lies beyond the walls of a room. But once we recognize that space and time themselves are intrinsic properties of the universe, the question loses its meaning. There is no coordinate system or metric that extends beyond the universe. Asking what is there assumes the very thing, the framework of space-time, that does not exist beyond the totality of the cosmos. Philosophically, this forces us to confront the limits of human reasoning. Our brains evolved to think in terms of boundaries, containers, and directions. But the universe as a whole may defy such concepts. We can describe what happens within the universe, the stretching of space, the motion of galaxies, the evolution of the cosmic microwave background, but we cannot describe what lies beyond, because there is no beyond in any meaningful sense. The universe is self-contained, and the notion of an external reality does not apply. This perspective also reframes common questions about cosmic origins. People often ask, what came before the Big Bang? Or what exists outside the universe? From a philosophical standpoint, these questions may be ill-posed, because time and space themselves began with the Big Bang. There is no temporal or spatial reference frame in which before or outside can be meaningfully defined. In other words, the universe is not merely an object within a larger context. It is the totality of existence, and our usual categories of causality and location do not extend beyond it. Yet this does not make the universe inaccessible or unknowable. Mathematics, observation, and theory allow us to describe its properties with extraordinary precision. We can measure the cosmic expansion, map the cosmic microwave background, quantify dark energy, and model the evolution of the cosmos from its hot, dense origin to its present state. Even if the outside is meaningless, the inside is rich with structure, governed by elegant and testable laws. The philosophical lesson is that some questions may be ill-posed, but others, those about the properties of the universe itself, are not only meaningful but answerable. This analogy of the North Pole also serves as a humbling reminder of human perspective. Just as explorers on Earth cannot go north indefinitely, we cannot situate ourselves outside the universe. Our observational horizon is finite, and our conceptual frameworks are rooted in the universe we inhabit. Yet by accepting these limits, we gain clarity. The universe expands, galaxies recede, dark energy stretches space, and time flows, all within the bounds of reality itself. We do not need an outside to make sense of these phenomena. They are internally consistent, measurable, and comprehensible within the universe itself. Ultimately, the philosophical angle encourages both humility and wonder. While we cannot peer beyond the totality of existence, we can marvel at the richness of what lies within. The universe is self-contained, governed by laws that are both intelligible and astonishingly beautiful. The question of an outside may be meaningless, but the expansion within is profoundly real, observable, and full of mystery. Recognizing the limits of meaning does not diminish the awe we feel. It enhances it, inviting us to explore the universe on its own terms, not ours. As we bring together all these threads, the expanding universe, the stretching of space-time, the cosmic microwave background, Hubble's observations, dark energy, the finite and infinite possibilities, and the philosophical reflections, it becomes clear that the universe is not expanding into anything at all. It expands within itself. The distances between galaxies increase, the scale factor grows, and space-time stretches. Yet there is no external container, no surrounding void, no beyond into which it spreads. This is not a limitation of our understanding. It is a fundamental feature of reality. The universe is a self-contained, dynamic entity, and its expansion is intrinsic to the fabric of space-time itself. To appreciate this fully requires letting go of ordinary intuition. Our brains are wired to think in terms of motion through space, edges, and boundaries. But the cosmos operates on a scale and in a manner far beyond these everyday experiences. Expansion is not motion through a medium. It is the evolution of space itself. Galaxies do not race outward from a central point. Rather, the metric that defines separation stretches, carrying everything along. The fabric of the universe is growing, and the universe grows with it, in all directions simultaneously, uniformly, and without an outside. This realization is both humbling and exhilarating. It reminds us that the universe is stranger and more magnificent than we can perceive directly. It is a cosmos in which the familiar rules of everyday experience are not absolute, yet the universe is consistent, predictable, and measurable. The counterintuitive concepts, an infinite yet expanding universe, a finite yet unbounded space, the role of dark energy, the cosmic microwave background as a relic of a hotter, denser past, combine to form a coherent, mathematically robust picture of reality. Each discovery, each measurement, reinforces the astonishing fact that the universe is alive with expansion, yet requires no external stage. In this sense, the mystery itself becomes part of the awe. There is a profound beauty in a universe that grows internally, in which space itself stretches and carries galaxies apart, in which time, space, and energy emerge together at the Big Bang, and in which there is no outside, no center, and no edge. These are not failures of explanation, they are triumphs of understanding. They show us that reality is not constrained by human intuition but follows elegant principles that we can uncover, explore, and appreciate. The expansion of the universe is more than a physical phenomenon. It is a lens through which we can glimpse the vastness and subtlety of existence. It tells a story of change, growth, and evolution on a scale that dwarfs human experience, yet is accessible to us through careful observation, theory, and imagination. It invites us to contemplate our place within a cosmos that is not static but dynamically unfolding, a universe that is not contained but self-contained, a universe that expands within itself, carrying all that exists along in a cosmic dance. Ultimately, understanding that the universe expands within itself, and not into some external void, allows us to embrace both knowledge and wonder. The universe is at once comprehensible and mysterious. Its laws can be described, its expansion quantified, and its history traced, yet it challenges the limits of intuition and imagination. The awe we feel comes not from the unknowable outside but from the richness of the universe itself, the intricate, expanding cosmos that surrounds us, that we are part of, and that continues to stretch, grow, and evolve in ways both observable and profoundly beautiful. The universe is a self-contained masterpiece, an ever-expanding canvas on which space, time, and matter interplay. Its expansion is not a journey into emptiness, but a story of the fabric of reality itself stretching and unfolding. This is the mystery and the wonder of cosmology, that everything we know, everything we observe, is part of an ever-growing whole, a universe that expands from within, carrying us along in its magnificent, ongoing journey. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.